Hello students, the topic that I am going to teach you today is diffraction of light with special reference to gratings. Now it is included in your BSc second semester syllabus both in DMU and also in MU. Now before we start diffraction, first let me explain a little about light. As in school you have learned about rectilinear propagation of light, that is, light travels in straight line. Now depending on that property, we have developed so many laws of reflection, refraction, lens laws, as well as optical instruments like telescope, microscope. Then why we need some other forms of light propagation, that is, light travels in waves. Now there are certain phenomena which cannot be explained by considering light as traveling in straight line. Namely, those phenomena are interference of light, diffraction, and polarization. Now to explain these phenomena, light no longer can be taken as traveling in straight line. We have to take wave nature of light, which was first explained and developed by Huygens long time back. Now this wave nature of light, though the mathematical formulation is lengthy, rigorous, as well as complicated, we are not going in details about the mathematical parts, but simply we are going to give the outline structure of diffraction. Now of course, as you go in higher classes, you will find that light has another nature also. We call that particle nature of light. Anyway, now the parts we are going to learn today is, first of all, what do we mean by diffraction? Then, is it different from interference? And how many classes of types of diffractions are there? And grating, experiments, its uses, and so on. Now, let us start the parts we are going to study today. That is, the first one is, what is diffraction? Now, whenever light encounters any opaque object or obstacle, we expect that there should be a sharp line of demarcation between the shadow region and bright illuminated region. However, if you closely observe, you will find that there is no such sharp demarcation between the shadow region and illuminated region. Always there is a part in the shadow region which is slightly illuminated, and there are certain alternately bright and dark regions. Now this bending of light around an obstacle, we call it diffraction. It cannot be explained if light travels in straight line. If light travels in waves, only then it can bend. That is why it is to be explained by the wave nature of light. Now let us come to the second part, that is it same as interference? Diffraction, interference, though they appear to be different phenomena, basically diffraction is also a type of interference. Only the difference lies in the nature of the sources of light. In case of interference, the sources which produce the interference pattern, they are two coherent sources from two primary wave fronts. Now you know the word coherent. Coherent means the light waves coming, they should have a constant phase relationship. Now it is possible only when they originally start from the same source. That is why we use the term coherent. Now, in case of diffraction, the interfering light waves, they should be from a single primary wave front. So basically they are same. That is produced due to superposition of light waves. Only slight difference is in their nature of sources and the observation we see on the screen. In case of interference, we see the interference patterns as lines. We call them fringes, interference fringes. These fringes may be straight or curved, sometimes hyperbolic. But in case of diffraction, we do not see fringes lines, but we see thick lines. We call them bands. Actually, they are a combination of lines. So basically, there is no difference, but the difference appears to be in their observations as well as in their sources of light. Now, coming to the third point, that is different types of diffraction. Now, basically, there are two distinct classes of diffraction. One is we call Fresnel type of diffraction, and the other is we call Fraunhofer type of diffraction. In case of Fresnel type of diffraction, the source of light as well as the screen where we are to observe, these two are at finite distances. Finite distances means they are very close. In laboratory, they are actually a few centimeters, a few feet away. And in case of Fraunhofer diffraction, the incident light, the source which gives the incident light, and the screen should be at infinite distances between them. In fact, there cannot be any infinite distance. So how to convert this infinite distance from a finite distance is, in case of Fraunhofer diffraction, if here the source is here and the light coming from the source is diverging in nature, and these diverging rays are made parallel with the help of a lens L1, such that distance between the source and L1 should be the focal length of the lens L1. Then the emerging light will be parallel. Now, parallel light means basically their source is at infinity. So we convert in this way the nearby source as infinite source. And then again, it passes through the obstacle, maybe lens or whatever, grating. The emergent light will again be parallel. We cannot focus it on the screen. It has to be focused at infinity. So how to convert this problem is, again we use another lens L2 as shown here, and the screen is placed at a focal length from L2 such that lights after passing through L2 will be converged on the screen. So in this way, Fraunhofer diffraction type is made with the help of two lenses such that we can observe the phenomena in laboratory. Coming to the fourth point, there is gratings. Now, first of all, let me tell you what is a grating. Grating is an optical device. Though it is very small in nature, it is one of the most versatile and commonly used optical instrument, or we say device. Now, grating, how it is made is, grating is actually a optically plain glass plate, which is of usually size 2 by 2 inches. On this glass plate, a number of parallel and equidistant rulings are made. Now, these rulings are made with a fine diamond head, and usually 10,000 to 15,000 rulings per inch is made. So it comes to about, say, 4,000 or 5,000 number of parallel lines in 1 centimeter. Now, practically, this making of grating is extremely difficult. So, we do not use the real gratings in the laboratories. Real gratings are very rare and expensive, and we use in laboratory the replica gratings, which is made of a plastic, transparent plastic. Even though it is plastic, it also costs a few thousands. Now, when we make rulings on the glass plate, the rule surface acts as, rule line acts as an opaque surface, and in between the two rulings, the clear or transparent surface, it acts as an opening, or we call that slit. So the light incident on the grating will be allowed to pass through the slit, and some part will be blocked at the opaque rulings. Since the slits are very narrow in nature, the type of the rate of diffraction or bending is also very high. And the theory of a grating is, in this given diagram, A, B, C, these 3 points, they represent the edges of the slits. Now, there are large number of slits. In fact, between 1 centimeter, there will be 4,000 or 5,000. So out of that, we take any 2 consecutive or 3 consecutive openings or slits represented by A, B, C. Now, this A, B, C, between A and B, the separation is width of 1 slit, which is given as small a, and width of 1 opaque object, opaque ruling, which is given by small b. So separation between any 2 consecutive slits, consecutive points, we call them corresponding points, that is A plus B. Now this small a plus small b, it is also known as grating element or grating constant. And this grating constant is also equal to the reciprocal of the number of rulings per unit length. So when a parallel beam of monochromatic light is incident on the grating surface, some of the rays will be diffracted and some of the rays will transmit without any diffraction. Now, after passing through the lens L, they are focused on the screen as shown here. Now, those rays which are not deviated or diffracted, they focus at a point O, which will be of maximum brightness. We call it central principal maximum. Then on the either side of central principal maximum, there will be also different maximum points as represented here by O1, O2 on one side, like that O3, O4, and O1 prime, O2 prime, O3 prime on the other side. So the screen will show a number of bright bands. The central one will be brightest. On either side of the central band, there will be alternately bright, dark bands. We call them central bright fringe, central bright principal, then first order principal, second order principal, like this. Now, if we consider a set of rays which are diffracted at angle theta, as shown here in the diagram, these rays, after passing through the lens, they focus at a point O1. If we draw a perpendicular CGS on the deviated rays, the distance BG will be the path difference between the two rays which are deviated or diffracted from the point B and C. It is very simple. By very simple geometry, we can easily show that this path difference BG is equal to BC sine theta, where theta is the angle of diffraction for this particular set of light. So this path difference A plus B sine theta, if it is equal to even multiples of lambda by 2, where lambda is the wavelength of the incident monochromatic light. Why we use monochromatic light? Monochromatic means the light incident has single frequency. So this monochromatic light having wavelength lambda, they will produce maximum interference, that is brightness, if the path difference is equal to even multiples of lambda by 2, that is equal to n lambda. Even multiple means twice n into lambda by 2, 2 cancels, n lambda. So the condition or the theory working principle for the grating is A plus B sine theta equals to n lambda, where n is natural number, natural integers. For the central maximum, n will be 0, and for the first order, n will be 1, second order, n will be 2, like this. So we shall see a number of lines on either side of the central maximum. And grating, why we study grating is, though it is a simple device, when we use it in optical spectrometer, it can calculate, it can measure the wavelength of the incident light. Wavelength of the incident light, it may be, say, sodium vapor lamp, or say helium light, or whatever light. If it is passed through the grating, it will produce the diffraction. By measuring the angle of diffraction in the optical spectrometer, and by knowing the number or order of the spectrum n, we can easily calculate this lambda, unknown wavelength. So grating, though it is a simple device, it has wide use in optical experiments, mainly in, say, light experiments to determine the unknown wavelength, like this. Now students, though they have very large lengthy calculations, here we have given just the outline, and if you have any further, say, doubt or query, you can contact to the given link below.